right. Yeah, thanks for the introduction. It's very nice to be back at MIT to talk about some researchy stuff we just produced at MegaETH. By the way, MegaETH is a super fast Ethereum rollup, layer 2. So the core feature is what we call real-timeness. Basically, we want to mimic the level of Web2 performance, like sub-millisecond transaction latency and up to 10,000 transactions per second in terms of throughput. But this talk, I think, is kind of standalone. It's not really just about MegaETH. It's a primitive that would be very useful for whatever blockchain that still hopes to get some what we call state commitments, basically Merkle Trie roots, state roots in Ethereum, or this Merkle commitment of all the unspent UTXOs in Bitcoin, so this kind of stuff. Yeah, so it's a very long title. I'll just shorten it to small authentication, large trie. This is the name of the data structure that we developed, and it's also kind of the essence of the protocol of the scheme. Basically, you want to capture a large amount of data with a very small authentication structure. So first, what is a authentication structure? What is the primitive that we're working on? So we call it the authenticated key value storage, and yeah, I think people in different communities, like cryptographers, they call it like authenticated database. I think system people, they call it authenticated key value storage. So basically, it's just a Merkle tree, right? So we have a bunch of key value pairs. For example, your account balances in Ethereum, or your unspent UTXOs in Bitcoin, whatever, right? But you want to capture. So for example, Alice has $10, and you want to compute a commitment. So think of it as a hash of these key value pairs of these individual elements of information. And the commitment is useful because you can generate a proof very efficiently and also verify the proof very efficiently that some particular key value pair or some particular data element belongs to the commitment. In the sense that, say, I tell you that the current state of Ethereum is captured by this commitment 0x.beef, and then I can very succinctly prove to you that my balance, for example, I'm Alice, my balance is $10 with just a very short amount of data. So this is why it's useful, right? It's basically what Merkle Trie allows you to do. And yes, so these kind of data structures, they also allow you to update those state elements. For example, Alice's balance increased by $10, and you can accordingly increase the commitment to reflect what's the current state. So why is this interesting, right? It's interesting because it's by far the most important performance bottleneck on Ethereum or any similar blockchain that still hopes to produce a up-to-date state commitment in real time. So what I'm showing here is the throughput, or I should say the amount of time for you to process a bunch of historical Ethereum blocks from the Ethereum mainnet on a machine with a relatively recent version of Wrath, the currently leading edge Ethereum execution client. So basically what you're doing is you are rerunning those Ethereum blocks, updating the state roots, and also doing other things in real time. And then we're measuring the amount of time it takes for you to finish the process. So the time is basically a metric for how performant this process is. And by the way, we also vary the amount of memory available to the server just to test different scenarios. So here, the green bar, the green section of the bars, is the amount of time taken by those re-execution processes to update and maintain the state roots, or to update and maintain the state commitments of those authenticated key value storages. So you can see that in the ideal case where we have virtually an infinite amount of memory for you to use, maintaining the commitment takes 5 times 7, 6 amount of time than it took the process to actually run the transactions. So basically, you execute a transaction that you spend almost 6 times longer to do all the maintenance work on the state commitments, which is arguably not useful work if you only care about transaction TPS, right? And the issue worsens to almost 10x when you have a limited amount of memory, which is usually the realistic case. So it's pretty tough because, yes, it's pretty tough because that basically says, hey, I want to build a really fast blockchain, and it basically says that if we don't worry about this authenticated key value storage, if we don't worry about like updating the commitment, then it seems that the best we can do is to remove the purple section and the blue section, and at most we kind of get a 10% improvement because we're not addressing the elephant in the room. So this is really a very important problem. And the reason that Merkle-Patricia tries or the standard state authentication like key value storage used by Ethereum or most blockchains is because they generate a ton of random disk IOs when you try to update them. So what you see here is each node in this Merkle-Patricia Trie data structure is the hash of its children. So, and also, the tree is structured in the sense that if you follow the path, so each edge in the path, each edge in the tree has like a label, a segment of your key or of your address associated with it. So if you go from the root and if you traverse the path that reconstructs your, say, your wallet address, then that's basically the list of nodes, the list of internal nodes that you have to update when you update your key. So basically, when you update your key, you have to kind of propagate all the changes back to the root because they're all hashes. You touch it, you have to touch all the nodes in the middle. And this generates a ton of random disk IOs. And worse still is sequential. So you cannot even like do it first and then hope to do all the remaining updates in parallel. It's impossible. You have to do it sequentially. And it kills performance on more than an SSD, which has a ton of IOPS or IOs per second when you do them in parallel, but not too much when you do them in a sequential way. So this is why Merkle-Patricia tries, or the state-of-the-art, or at least the status quo data structures are not very ideal when it comes to speeding up updates or speeding up like updates to the commitments. But they also have some nice properties. For example, they are what we call history independent, in the sense that the state root is a pure function meaning that there's nothing else like involved in the computation but of the actual state elements that you want to capture, like the account balances. Also, Merkle-Patricia tries are easy to maintain in the sense that it does not really burn a lot of CPUs or memory or disk space or a lot of bandwidth. So the wish list for us is to keep the nice properties of Merkle-Patricia tries, but try to minimize the disk I/O because this is what makes like updating state roots 10x slower than executing transactions on Ethereum. So a crazy idea here is, hey, can we store the entire trie, the entire Merkle-Patricia trie, or whatever data structure, in a reasonable amount of memory? Because if you can fit everything in the memory, then there's there's no bottleneck from like the sequential disk IOs, right? We kind of skip, you kind of get around this random IO issue altogether. So to see if that is actually feasible, there's a very important metric, which is the amount of data you have to store for per state element you want to commit to. In the sense, so we have heard of this state bloat issue, right? Ethereum state keeps expanding and is going to say 10x in the next, say, 3 years. And with that, it seems that the size of the state commitment data structure, the size of the authenticated key value storage will also expand by 10x. And at some point, you cannot fit it in the main memory anymore. For now, it's possible. It's about, say, 100 gigabytes. But very soon, it may not be possible anymore. So the key metric we optimize here is that we want to commit to an ever-expanding, a large amount of state elements or accounts or UTXOs with a relatively small like auxiliary data structure, the authenticated key value storage. We want to minimize the amortized cost of this authenticated key value storage data structure per state element that we commit to. So let's take a look at how Ethereum Merkle-Patricia Trie fares. So in this case, Merkle-Patricia Trie has about 16, exactly 16 children per node. And the number of levels in this data structure, or how large or how tall this data structure will be, is roughly the number of nodes or the number of state elements you capture divided by your depth. Sorry, your width, which is R. Sorry, I think there's some formatting issue. But basically, in the ideal case, actually, to capture, say, 1.5 billion keys or 1.5 billion addresses, you only need about 3.2 gigabytes, which seems nice. But again, this is the ideal case. In the realistic case, because there is something which we call sparsity in Merkle-Patricia tries that makes the actual data size of Merkle-Patricia tries much larger than this ideal case. So in particular, we found that when you go deeper and deeper into this Merkle-Patricia trie, there are fewer nodes, or each node has fewer children. And when a node has less than 16, which is the optimal, the maximum number of children it has, it can capture a smaller number of children, right, by definition. And because each node is managing a smaller number of children, if you ultimately want to handle the same number of accounts or nodes in the bottom layer, you have to add more nodes in the middle because it's because each node has less children. Right? Each node is managing a fewer. Each internal node is not doing its best capturing the hashes of its children. So you have to use more of them, and that expands, that kind of inflates the number of internal nodes, and the size of the tree just expands. And here is some theory and some experimental data. So the points are from our experiments, and the curve is derived by some theory. And the optimal case is the black curve, which is on the bottom. And the realistic case is the green curve here. And you can see that there's almost a 8 times difference from optimality to the reality. And in Ethereum's current size, 1.5 billion keys, you need almost 17 gigabytes to fit all those internal nodes. It's just the internal nodes. So there has always been a proposal of, say, vertical tries, where the essence is basically you expand the width of the tree to make it fatter but shallower. And in theory, that should help you reducing the number of internal nodes. But it seems that because of the same issue, because of the sparsity, the effective is limited, and from the optimality, which is the black curve, vertical tries, basically 256 array radix tries, they don't do so well either. And we even proved in theory that even if you just keep expanding the width of the tree to compact it, to make it even shallower and shallower, you only achieve so much. So the purple curve is the average case at different arity or at different width of the tree, and the vertical bar, the y-axis, is the size of the data structure divided by the number of keys, basically the per key per account overhead when you want to authenticate them. This reduction stalls at some point, even if you keep increasing the arity, and the trend actually goes on, just goes horizontally. Where the optimal case, which is to use a complete, perfect, balanced tree, you get you keep getting effectiveness as you increase the arity. So it just says that just blindly expanding the width of the tree does not really help. So so what we have learned so far is that we want to minimize the disk I/O when you commit to, and when you update the state commitments of your blockchain. And the idea to circumvent this random disk I/O issue is to fit the entire authentication data structure in the main memory. And the key metric we optimize for is to reduce the amount of overhead in terms of bytes per state element committed or per address or per key to a minimum. And the challenge here is that if you just blindly follow the what traditional algorithm or data structure people tell you, which is to expand the width of the tree, you hit a block, which is sparsity, and that kind of limits how much you gain from these protocols, from these schemes. So what we did is we found that actually there is a trick that can take which are not elaborate, but basically what we learned was that a perfect data structure should be heterogeneous in the sense that you should divide your data structure into two parts. One, a static main trie, which is complete, basically what computer scientists are hoping for, in the sense that all the nodes inside this static main trie is complete and has all the children it should have filled with. And then you replace the bottom layer, which is plagued by sparsity, with hash tables. Hash tables are nice because they deal with sparsity very gracefully. They don't really expand in number of layers. You just resize the hash tables, and it can accommodate a different number of elements fit inside without really incurring extra work. Basically, that's the way I would summarize. And so this is basically our data structure. We have a main trie, which is complete and shallow. No spaces being left, no spaces being wasted because it's complete. It only covers the top layers, which is not plagued by sparsity. And yes, and then we have the buckets, which are hash tables instead of subtrees. These layers, usually in normal trees, in normal MPTs, they are plagued by sparsity. But yeah, hash tables are immune to that. And you just fuse them together, you get a very nice data structure. I will skip through the process of using this data structure, but you ultimately get a very nice data structure that outperforms Merkle-Patricia tries or any variant of it by almost 16x. So here, again, I'm showing the reality with Merkle-Patricia tries, which is the blue curve, the purple curve, which is Merkle tries in theory, and the optimality, which is complete trees, which is the dream of every computer scientist. But if you look at our data structure, which we call SOT, it kind of approximates, it approaches the optimality when the number of keys is large enough. And here it's about 10 billion. So basically, in the case where we actually care about, which is about 10 billion accounts, and also going from that beyond, we approach what you can do optimally with those authenticated key value storage data structures. Yes, and we did a bunch of, we actually took an implementation in our testnet, and we did a bunch of tests. And it shows that the new data structure completely gets us around this random disk I/O bottleneck, and the I/O bottleneck is no longer an issue for us. And it has slightly increased computation cost compared to Merkle-Patricia tries, but it's manageable, and it's parallelizable. So if you just throw more CPU cores, which is very easy to do, relatively easy to do, you get to higher throughput. And we also compared it with a few other recent works on solving the same problem, QMDB from, I think, Layer 0, and NOMT, I think, from Sovereign Labs. And we found that our performance is better than theirs at a cost of slightly, again, increased CPU consumption. But again, CPUs are cheap. Disk I/O is very hard to scale. So this is kind of the approach that we're taking. And yes, so short on time, so I'll just pause here. It's been live since day one of MegaETH testnet this March, and we're going to ship it in mainnet very soon. Yeah, if there's a Q&A session, I can take a few questions on the stage or offline. Yep.
Sorry, I didn't hear what date you're shipping. I didn't hear which date you're shipping.
Oh, I didn't say what date we are shipping, but yeah, it's a nice question. Very, very soon, yeah.
Thank you.